In recent years, the rapid rise of multimodal generative AI has transformed industries, from advertising and customer service to content creation and design. But with this explosion of synthetic visual content comes a critical challenge. How do we reliably evaluate the quality, safety, and alignment of these outputs? Human evaluation offers the gold standard, but it's expensive, slow, and impossible to scale. That's where MLLM-as-a-Judge comes in, using powerful multimodal large language models to automate the evaluation process at scale. These models analyze images and text together, assessing things like image quality, safety compliance, and semantic alignment with a given prompt. But here's the problem. Most current judge models are built for one specific task, like detecting unsafe content or measuring image sharpness, and they struggle when asked to handle anything beyond their narrow domain. They're like specialists who can't adapt when the rules change. And worse, many rely on supervised fine-tuning, which teaches them to mimic surface-level patterns, like memorizing a particular prompt format, rather than understanding the underlying logic of evaluation. As a result, they fail when faced with new or slightly different tasks, especially those that require reasoning. To solve this, we introduce MTRL-Judge, a unified multitask reinforcement learning framework that trains a single judge model to handle diverse evaluation tasks simultaneously, while learning why to judge, not just how. Let's break down how it works. First, instead of training separate models for safety, technical quality, naturalness, or alignment, we aggregate all these tasks into one large, unified dataset. The model sees examples from all domains, pointwise judgments, pairwise comparisons, image-text matching, safety detection, and more. But here's the key innovation. We don't just train it to predict the right answer. We train it to think first. Using a technique called Group Relative Policy Optimization, GRPO, the model generates multiple reasoning traces for each input, each one a step-by-step internal monologue, before producing a verdict. Why does this matter? Because when a model reasons before answering, it's not just memorizing patterns, it's internalizing the logic of evaluation. It learns to ask, does this image follow physical laws? Are the details consistent with the description? Could this content be harmful? This is where reinforcement learning makes the difference. Our reward function has two parts. Accuracy reward, did the final label match the human judgment? Format reward, did the model generate a proper reasoning trace before the verdict? By combining both, we incentivize not just correctness, but correct reasoning, a crucial step toward building trustworthy, interpretable evaluators. Now let's look at what happens in practice. We benchmarked MTRL-Judge against several strong baselines: a zero-shot off-the-shelf model, single-task SFT judges, unified SFT judges, and even single-task RL judges. The results are striking. On 6 diverse tasks, including image-text alignment, safety detection, and technical quality, MTRL-Judge consistently outperforms all baselines. It achieves state-of-the-art performance across the board, with gains of up to 4.6 points on rationality assessment. But the real test wasn't just on familiar tasks, it was on unseen formats. We evaluated the models on MJBench, a dataset designed to test generalization. Unlike the training data, which used single-image pointwise judgments, MJBench requires pairwise comparisons. Given 2 images, which one better matches the prompt? Which one is safer? This is a game-changer for real-world deployment, because in production, evaluation formats evolve constantly. And here's where the difference becomes clear. The SFT unified model, despite being trained on multiple tasks, plummets in performance. On the safety task, its accuracy drops to just 49.4%, worse than the zero-shot baseline. Why? Because it learned to recognize the format, a single image, one label, rather than the meaning behind the judgment. But MTRL-Judge, it adapts seamlessly. It achieves 82.23% on the safety pairwise task and 60.59% on alignment, outperforming all others. Why? Because the model didn't just memorize the format. It learned the principles of safety and alignment. It understands that unsafe means harmful content, regardless of whether you're comparing one image or 2. It can transfer its knowledge across formats. This isn't just about better scores, it's about robustness. In industrial settings, you can't afford to retrain a new model every time the evaluation pipeline changes. You need a judge that generalizes, explains itself, and scales. And MTRL-Judge delivers on all fronts. It's efficient. One model replaces dozens of specialized judges. It's effective. It matches or exceeds single-task specialists while handling broader tasks. And it's generalizable. It adapts to new formats without retraining. More than that, it's explainable. Every judgment comes with a reasoning trace, visible, auditable, and human understandable. This transparency is essential for trust in high-stakes applications like content moderation, medical imaging, or autonomous systems. So what does this mean for the future? We're moving beyond narrow, brittle evaluation systems. We're building intelligent judges that don't just follow instructions, they understand them. That reason before they respond. That generalize across domains. MTRL-Judge isn't just a new model, it's a new paradigm. A unified, reasoning-driven, multitask evaluator trained with reinforcement learning to think like a human expert. And it's ready for real-world deployment. If you're working in AI safety, content quality, or automated evaluation, this is the future. A single, powerful, reliable judge that grows smarter across tasks, not just whiter. Because in the age of generative AI, the most important model might not be the one that creates content, but the one that judges it. This work was developed at Meta AI, in collaboration with Hong Kong University of Science and Technology and Emory University. For more details, see the paper on archive.